بسم الله الرحمن الرحيم والصلاة والسلام على أشرف المرسلين. Now with the most recent, most important, most efficient algorithm in advanced machine learning, which is XGBoost. It's the next level of the boosting algorithms, and it's a recently developed algorithms. It's back in 2014, and like the XGBoost, it works based on stacking algorithm after the algorithm and try to adjust or deal with the errors made in the previous algorithm attempt to do the prediction or the classification. In this example that we are trying to clear some issues, because there is truly an issue here, we are going to see it in practice with an example. So, well, this is our data. When you look at it, it doesn't look like truly data. So let's go to our Obsidian nodes and we see our data set. This is our data and this is our representation. X is the, as you see, the input. This is the output. This is what we are going to predict later. So 10 with -10 and etc. We have this not 0.5. What is it? Here it says by default XGBoost starts by 0.5. Okay, and not to forget that we are going to make a prediction of a continuous value, so it's a regression, and we are going to do decision trees. This is why earlier when we were speaking about decision trees, I mentioned that they are also used for regression. So back to that 0.5. So the idea of XGBoost, not like XGBoost, where we were dealing with the probabilities, where we give more probabilities for the misclassified rather than the well classified. Here there is a new philosophy. So we start by a dummy prediction. As you can see, this is 0.5. It's arbitrary, and then we see the errors, and then we try to predict or understand how these errors are happening and try to reduce them. Concerning this 0.5, in literature you might find it not like this, just a default. We can find it by finding the mean. If we go to our data set here, we easily can see that 7 is gone with -7. We have 8 plus -10, it's -2. We divide it by 4, it equals -0.5. So we can say that the dummy prediction we did equals to the not or -0.5, but in our case we picked the 0.5. So this is the X, this is the Y, this is the dummy prediction, and these what we call residuals. This is the data set that the classifiers or the decision tree will be built upon. And how we measure this? It's simply the true value minus the prediction. The prediction, all of them are 0.5, so I just make a subtraction and we find these. So when you go back to the slide, now I think you understood where did these values come. Here they are. and this what are we called residuals, and this what will be the decision tree be based upon or built upon. So the data that we are going to be splitting is these. So we are splitting the residuals. We are trying to make predictions based on the residuals, and later we will see how it will be used. I hope this is clear for now, so there is no mystery here. Now similarity. This sim is the similarity. And why I saw that there is an issue here, when we come to the similarity, we can see two formulas and they are not the same, and I think it was a typo. So this one is totally different from this one. We will see which one truly gives 4, and you will understand it by yourselves. So what does this say? Sum of residuals squared over number of residuals plus alpha, and for simplification we've got alpha equals to 0. We come to the residuals and do the summation. 7.5 and minus 7.5 are gone. Minus 10.5 plus 6.5, it's a 4. 4 squared is 16, divided by 4 is 4. This is the similarity. So please pay attention here when you work on your exercises. This is not correct, and this is why I found it very important to make this video, because without having this clarified it might lead to true confusion. So now we understand all that exists here. Let's start to split the leaf into better leaves. For this we will try all possible and choose the best leaf. Well, this is our data set, and you are familiar now with decision trees. We are going to try and divide them, and this, since it is a regression, we are going to make a new strategy. We will try to divide by pick a point to divide our data and see the similarities. So the similarity of this data equals to 4, and it's very low since they are centered around the 0 axis. Now if we pick the division of our data, always the division is based on the x-axis. So when x is less than 15, on the left we will not say we have minus 10, but we pick the residual related to that point. That residual is minus 10.5, minus 10.5. The rest are on the right side. We have 6.5, 7.5, and minus 7.5. We will do the same. We measure the similarity of this and the similarity of this one. This squared over 1, you will find it directly. I'll bring the calculator to see that in practice. So we have 6.5 multiplied by 6.5, because 7.5 minus 7.5 is gone. This we will divide it by 3. Sorry. Let's check whether it's 6.5. Sorry, I actually didn't make attention or pay attention to what I was writing, yet it was right. So always we do the sum of this, we square them, we divide by the number. Since lambda equals to 0, this is gone with this. We got only 6.5 squared multiplied by 6.5 divided by 3. We've got 14.8. This is the 14.08. So I hope now this is clear. The gain of the original data, how did we get it? It equals the left plus the right plus the root. If you remember, we've seen the gain before, and it's something that we should have it positive. And why we are going to deal with this? So we took the division at here, then we will do the same here between these two, and then we move here. We try all possible splits and find which gain is higher. So we started by x is less than 15. The gain equals to left similarity plus right similarity plus the root similarity. It's 110.25 plus 14 minus 4, and I think it's obvious, it equals to 120. We will do the same for, as you can see here. Now we moved our separation line here. Now as you can see, the residuals are divided into two. As I told you, we are not picking the data, we are picking the residuals. That was a 7, now it's a 6.5. That was a minus 10, now it's a minus 10.5, and etc. We will calculate the similarity from here, similarity from this side. You remember I told you the similarity, it's the like a mirror, since those 2 points cancel out each other, it equals to 0. But here they not pretty opposite to each other. Now we calculate the gain here, and it equals to 4. I think I did all the calculations of, I have all the numbers. No, I didn't do that. So we've got 4. Voila, and 4x is less than 25. I'm not sure if it is mentioned here, the 25. No, it's the 30. So we did it for 15, we did it for 21, and now for 30. Whether it is 30 or 25, it's gonna be the same, because we created the same splitting, and it equals to 56. Here it is the 56.25 or something. I suppose you understood how we calculate all of this, and this is what is going to be asked from you. Now which splitting we are going to choose? We are going to choose the one with the highest gain, since the gain for x less than 15 is more than the others, so it represents the better split, so we take it as the better split. Sorry, now that we decided the first split, we are going to proceed to the next splits, but let's bring up a very important concept. Since since the gain is more, so it represents the better split. This is the first split. We do the same process to the leaves, so we did this split, it divided it like that. So later we need to divide this, so we will pick a line somewhere here. We do the same process as we did for the original residuals. So we take a cut here and we measure the similarities and the gain. Then we do the same, measure the similarities and the gain. We pick the best or the highest gain for the split, and so on. Let's come to where we stop it. We will do the same process to split the leaves. The stop criterion, where we will stop while splitting, because over splitting it will lead to complexity of the tree and some misbehavior or overfitting. So we introduced a parameter called gamma. This gamma is called the tree complexity parameter. So as you can see, this is a trade-off. This is something we pay for, this is we gain. So in any trade we try to make the action or the trade positive. If the gain is less than the complexity parameter, so it's going to be negative, it means that we should stop. We are not going to gain anything. The expenses are more. But if the gain minus that complexity factor is positive, we are allowed to keep dividing. And for default we take it as 130, and it's going to be tuned. This is a hyperparameter that we are going to be tuning also with lambda, but by default we take it, for simplification of by default we take it as 0. So as we spoke earlier, of course we tested the possible splits. We found out that splitting at 30 is the best. You remember our original data is here, so we split here, so we will have 6.5, 7.5 on the left, as you can see here, and minus 7.5 on the right. We measure the similarities. Now this is done. This is used to decide, so it's okay. Now let's explain what is these outputs. This is minus 0.5, it's one single element, so it is the output. Here we stop it. Why we stop it, and this is worth mentioning, we are supposed to come here and make a new split. So we have two possibles, whether we leave it as it is or we split it. You measure the gain and subtract from it the 130, you will find it negative or null, so it is not useful, so we are not going to keep. This is mentioned here. It is not deduced, it's calculated, but it's just have been put here briefly. So it says it's going to be negative, so we stop splitting. We don't need to split any further. So since we are not going to split, this should be the output. So it's the it's going to be considered as the final leaf. This is okay, it's one single element, it's final leaf. We take its value, which is minus 10.5. It's the same for this, it's the output, but for here we are going to take the mean, the sum over the number, which equals to 7. And you can see it here, and by definition we take the lambda, but since the lambda here, so sorry, it's not the mean exactly, but for simplification it was the mean. So since the lambda is 0, we sum and divide by the number, so this is why we got 7. Now let's move to make prediction. Now here we build our tree, the first tree. So to understand what we've done, we got the original data, we did the dummy prediction or default prediction, we got the residuals, then we try to split the residuals into branches, two leaves, so we get the best gain, of course. And this gave us the structure of the tree, and that tree at the end is going to be used for prediction. We started by a prediction dummy. Now this tree will give us the new prediction, and this is the rule for the prediction. Let's see, where is it exactly? It's supposed to be here. Well, I was trying to find out the formula from well written, but it's obvious and easy. This is the old prediction, which equals to 0.5. We add to it, this is what we are going to try to fix. This is the old prediction, and we try to find out the new prediction for the four input data. So the learning rate is going to be given or default, but as you can see, it's a hyperparameter to be tuned. So it all equals to the old prediction plus the learning rate multiplied by the outputs. So this is for the first one, this is for the second and the third, and this is for the seventh. If we go back to our data set, so for 10 we are going to use minus 10.5. For 20 we are going to use 7 as an output, for 22 7 as an output, and for 32 we are going to use minus 7.5. It's repeated here, so I was kinda wasting the time. Well, the prediction of the first point, as I told you, it's the old prediction plus the learning rate multiplied by the residual at that point, or the residual of that input, and it equals to minus 2.65. This is the old prediction, this is the new prediction. Let's compute the residual now. The residual was minus 10.5. As you can see, the new prediction is minus 2.65, and the new residual, when we do the subtraction, we will find it equals to this, which is the new residual. And as you can see, it's smaller than the old one. Doing the same for the other data, we will find the new residuals based on the prediction. So we measure or calculate the prediction. As you can see, the first prediction, the second, where is the third, is not here, and this is the fourth. Then we measured the new residuals. Now that we have the new residuals, and if we compare them to the old one or the old ones, it's obvious they are getting smaller, and this is the goal of the XGBoost. As you can see, the new tree minimized it's the first tree, so we can say the new tree. It's the first tree minimized the residuals comparing to the initial prediction using 0.5. Now, based on this new residual, we create the second. So if you understood what we did, this is what going to be our new data, and we will do the same process as we did before. We split, we calculate similarities, we calculate the gain, and see which is the best split, and then we stop when the gain minus gamma is negative, then we do our predictions, we calculate our residuals and see how small they become. Now, and based on the new residual, we create the second tree with the same process to minimize more the residuals and so on. So this was the first. Now we inject these to the new tree, then we keep doing the same until make new trees until the residuals become small or we reach the maximum of the trees. So as I said, we will keep creating trees, and we stop here. It says make new trees until residuals become smaller or reach the max number of trees. Reach the maximum number of trees, it means that we decided beforehand the number of trees, so when we reach it we stop. Or when the residuals become smaller, it means, if you remember that elbow thing, when you see that the models that you add are not bringing anything or significant improvement, we stop there. And this is for real applications, not for you or for understanding or practical work. And just back to the predictions, you remember this is the previous prediction. For all of them it was not 0.5, but later you will take the new predictions and use them. So as you can see, it's not going to be one single one. You are going to have a prediction of the first element with its output and so on. If you understood this, I think it's going to be more than enough. And the most important is that issue we had with the similarity, because I didn't pay attention to it, so I hope you understood it. So it's this one and not the other one. And good luck and see you.